Okay, so we're back here for part 4. Now, still section 10-2, but now we're going to talk about a significance test for comparing two means. We just did the confidence intervals. We're going to use the same problem that we just did. And the problem, this was Mr. Wilcox's class, talking about students drinking caffeine versus non-caffeine, and then looking at the change in their pulse rates. And so we're going to take this problem, and now using the caffeine minus no caffeine problem, is the mean change in pulse rate significantly higher for the students who drank caffeine? So is it higher for the ones who drank caffeine than the students who did not have caffeine? So now we're going to do a significance test. And in this case, for a significance test, this is where we use the acronym PHANTOMS. So we have our parameter, our hypotheses, the assumptions, we name the test, we find the test statistic, and we obtain the p-value, and then we make a decision and we state our conclusion. So the parameter is going to be the same that we did before. So the parameter is going to be mean 1 minus mean 2 is the true difference in mean change in pulse rate. And we're doing caffeine minus no caffeine. So the true difference in mean change in pulse rates. So this is for caffeine, this is no caffeine. Our null hypothesis is that there is no change, is that the difference of those values, of those true mean changes, is 0. But what we suspect, our alternative hypothesis, is that the true difference in the mean change in pulse rates is going to be greater than 0. In other words, we think that the true mean for the caffeine drinkers, their change in pulse rates is higher than the true mean change in pulse rates for those who did not drink caffeine. So there's our null hypothesis, there's our alternative hypothesis. Now the assumptions, we made the assumptions, it's the same thing as we did on the other side. They are not, the students were not randomly selected, they volunteered. However, they were randomly assigned the treatments. So the random condition is okay. That also takes care of the 10%, the independence rule. And we also did the normal condition, even though both sample sizes were 10, they were both less than 30. Because when we graphed them, we could say the graph was not heavily skewed. I used a box plot, not heavily skewed, and no outliers. So we can use the normal approximation to do this. Now, we're doing a test, a significance test. So this is a two sample. This is a t-test for a difference of means. This is a two-sample t-test. So we did a t-interval in the last video. We were doing a confidence interval. Now we're going to do a test. So it's a two-sample t-test. Okay, so now we need to obtain the test statistic. And the test statistic, in this case, is going to be our t-value. On your formula sheet, they do give you this. They say the test statistic is equal to, we take the statistic minus the parameter, the true, in this case the true mean. This would be the sample mean, minus the true mean, divided by the standard deviation of the statistic, which in this case is the standard error. Now this is a t-value. We would use z if it was proportions, or if we knew the actual population standard deviation, but we don't know that. T is equal to the statistic is going to be the difference in the sample means. So that would be sample mean 1 minus sample mean 2 minus the true population means, so mean 1, mean 2, minus mean 2, over the standard deviation of the statistic. Well, that would be our standard error. We take the sample standard deviation of the first sample squared divided by n1 plus the sample standard deviation of the second sample squared divided by n2. And we had the values. I'll just put them up here. So we knew that the mean of the first sample for caffeine was 3.2. The mean of the second sample was 2.0. The standard deviation, sample standard deviation of the first sample was 2.6998. And the standard deviation for the second sample, for those who did not drink caffeine, was 2.6247. So we can go ahead and calculate this now. So we're going to subtract the sample means, which is 3.2 minus 2.0. So we will get, that's 1.2 minus. Now the thing is, in our null hypothesis, we are saying that the true mean difference is actually 0, that there's no difference whether you drink caffeine or not. So this number here is 0, which is nice, divided by the standard deviation of the statistic, which was 2.6998 squared. The n values were 10. Both sample sizes were 10. And then plus 2.6247 squared divided by 10. So now this becomes a calculator problem. So 1.2 minus 0 is just 1.2. Let's see, wait, let me make that a fraction. 2.6247 squared divided by 10. And the test statistic is 1.0078. 1.0078. Okay, so we've got the test statistic. We need to use that to obtain the p-value. When we look at a t-distribution, it's similar to a normal distribution, not quite the same. And in this case, we're looking where the t, so the t-statistic is 1.0078. Now you have to think, well, okay, am I looking at the right tail or the left tail, or are we looking at both tails? If our alternative hypothesis is that the difference is positive, the difference is greater than 0, then we're only going to look at the right tail, where we have our greater values. If the null hypothesis was less than 0, we would only look at the left tail, where we have the lower values. If this was not equal, we would have to look at both tails. Okay, but in this case, we only need to use one tail. Now, the degrees of freedom, we're going to use 9. Both samples were 10. If one of these was lower, though, we would use the lower sample size and then subtract the 1 to get the degrees of freedom. And we can use a TCDF. Where the lower bound would be 1.0078. The upper bound, I'll just make that 1,000. And the degrees of freedom is 9. Okay, paste that. So here's TCDF. I'm going to write down everything I just did. Made that 1,000. Degrees of freedom was 9. So this was the lower bound. The upper bound, degrees of freedom. Enter. And we get 0.1699. 0.1699. That is our p-value. So we have our test statistic and we just obtained the p-value. Now remember, the p-value is the probability, assuming that the null hypothesis is true. So assuming there's no change, there's no difference in the true means in the change in pulse rates. The probability that we would get a test statistic here or higher or more extreme is going to be 0.1699. Now the last thing we do here, we've done the test statistic, we've got the p-value. We need to make a decision to either reject or fail to reject the null hypothesis. Since the p-value of 0.1699, now I didn't put a significance level here. I didn't tell you what significance level to use. If that's the case, then we're going to use alpha equals 0.05. Okay, we'll just use the 0.05 significance level. Since the p-value, is greater, sorry, it's not less than, it is greater than alpha. So since this is higher, what we're saying is that it's not that unlikely that we would get this mean difference. It's not unlikely that this would happen. There's a 0.17 chance, a 17% probability that we could get a difference like this if the null hypothesis is true. So since this is higher than the significance level, we fail to reject the null hypothesis. We fail to reject it, so we say there is not convincing evidence that the true difference in the mean change of pulse rates is greater than 0. There is not convincing evidence that the true difference in mean changes of pulse rates is greater than 0. And again, I'd want to say this is caffeine minus no caffeine for that. So even though our sample mean was certainly higher for the caffeine drinkers, our significance test is saying, well, yes, but that could have been achieved by random chance. The p-value, there's a 17% chance that this happens randomly, that we get this value or higher if the null is true. So we cannot reject the null hypothesis, and so we say there's not convincing evidence that the true difference in the mean change of pulse rates is greater than 0. Now, if I had done this with the calculator, which would have been much faster, stat, test, this is a 2-sample t-test. And now I already have the data in here, but let's say I go to stats. And, well, it's already typed in for me, but I could have typed it in myself. In this case, the significance test is greater. We're not pooling. So we do not pool for the standard deviation. We only do that for proportions, for 2 proportions. We don't do that for means. And we calculate, and there we go. There's our test statistic. Here's our p-value. Now notice the p-value is a little bit lower, 0.1635. The degrees of freedom, they used 17.99 degrees of freedom. So if you're using the calculator, if you're doing the 2-sample t-test, make sure you do write this information down on your exam. But we're coming up with the same conclusion. Last thing to comment on is that in the previous video, we had done the confidence interval. And with the confidence interval, since we had from negative to positive, 0 was a plausible value, we would have to say there's not convincing evidence that the true pulse rate change from caffeine is higher than the pulse rate change from no caffeine. That's exactly what our significance test is saying, is that we cannot reject the null hypothesis. The null hypothesis was that there was no change in the true difference of the mean changes in pulse rate for that. So our significance test is agreeing with our confidence interval. And that is the end of the notes.